All right, guys, I am here to give you some notes about dynamic crust. So we're going to first start with me finding what I wanted to show you. Here's our PowerPoint. So hopefully you were able to watch the video on Alfred Wegener first, answer the questions on page 1 about Alfred. I say Wegener, but you know me, I never pronounce anything correct. So it's Wegener. He is known as the father of plate tectonics. So back in the early 1900s, he believed that the continents of South America and Africa, if you kind of like cut them out, I don't know if you did this in 6th grade, if you cut them out and put them together like puzzle pieces, they look like they fit together like jigsaw puzzle pieces. But he was laughed at, and people didn't believe that. And he was like, well, you know, there's mountain ranges and they only form on the edge of continents. And it was really hard to prove because everyone thought that mountains formed when the earth cooled and kind of shriveled up. Like if an apple became kind of rotten, the skin would shrivel up. So he actually died and no one accepted his theory. It wasn't until the 1950s that people started being like, you know what, this guy, he had a point. Okay, so you're going to watch those questions and answer the questions in your notes on continental drift. Right here, you're going to answer these questions. Answer these questions about Pangea, and as it started to break up, you'll notice they gave names to continents of current day continents, and you're going to see what happened to the start of the Atlantic Ocean, and then what's happening currently to the Atlantic Ocean, what's currently happening to the Pacific Ocean. So in the 1950s, there was evidence to support Alfred Wegener's theory, and again, he was long gone. So number one piece of evidence is the puzzle pieces that South America and Africa fit together like jigsaw puzzle pieces. Then there's similar fossils that you have fossils that match up in South America and in Africa that if they were broken up, these fossils wouldn't have existed in different continents. So you have that, and you have continental drift showing that in the 1950s, they had technology such as sonar and radar, and they could actually map the bottom of the Atlantic Ocean, and they were seeing this ridge here that was, or they didn't see it, they can sense it with remote sensing and see that heat was coming up and that the Atlantic Ocean is actually spreading and moving apart. So that was continental drift adding evidence. And the Ring of Fire, where all your plate boundaries meet, those are places with extreme earthquake activity and volcanic activity. So those are all pieces of evidence that you're going to see. Okay, so page 5 of your reference table, I would like to go over right now and go over your 3 main types of boundaries: convergent, divergent, and transform boundaries. So I have my Cami open so I can draw with you. Okay, let's get rid of this. Let's get drawing out here. Okay, first of all, we're going to start with the Mid-Atlantic Ridge. So you are seeing me color this Mid-Atlantic Ridge is actually an area of higher elevation underneath the water where the plates are splitting apart because they're diverging. But as they split apart, it's kind of like when you have a cut, blood comes up. Instead, though, the ocean floor is a cut, magma comes up. And it solidifies and solidifies, and it kind of makes this like ridge, higher elevation, and then pushes the plates away from that ridge. It's really cool. If you Google Earth it, you can actually see the Mid-Atlantic Ridge. And if I have some time at the end, I will show you. So you have ridges all over the place. You have your East Pacific Ridge splitting apart. The Southeast Indian Ridge also splitting apart. Okay, so that is known as a divergent plate boundary, where the plates will move in opposite directions, and as they do that, they rip open the ocean floor and magma comes up and solidifies. Now we have convergent plate boundaries. Okay, so you have convergent plate boundary that I'm outlining right here in blue with these boxes. These boxes here. So the boxes, if you look down at the map key, the boxes mean the overriding plate. And the side without the boxes is subducting plate. Subducting means to go under. So if you were looking at a profile, the subducting plate would go all the way under and the overriding plate would go and get pushed on top. And as that happens, you get like mountain ranges that occur. But because you have subduction taking place, you have melting of that floor. And whenever you have melting of rock, you create magma. And these mountains can be volcanic mountains. So you're going to notice most of the land plates, like the South America plate right here, this is all land. It's going to be the overriding plate because the land is less dense and the ocean is more dense. And you can see that on page 10 of your ESRT. It will show you that the ocean has a density of 3.0 and the land has a density of 2.7. So you have this overriding of the land and subducting of the ocean, which is going to cause mountain ranges. And in South America, that's your Andes Mountains. Okay. You will also notice that you might have two oceanic plates that collide. Well, one of those plates might be a little more dense than the other, and you will get a ring of, or not a ring, you'll get a chain of islands, and that's like your Aleutian Islands in Alaska, or your Philippine Islands, or their Japan Island. All of Japan is an island, so that's what's occurring in those areas. The only place where subduction does not take place is where two land plates collide. There is no subduction because these land plates have the same exact density, and you get huge. You get the biggest mountains in the world. You have Mount Everest. Okay, this is the Himalaya Mountains. So the largest mountains in the world caused by those two plates colliding, and there is no subduction that takes place. Okay, so you will answer those questions here. And then you're going to look at those three different types of plate boundaries, ocean to ocean. You can think of, Japan. Where's my writing? As an example, one plate will subduct, the other plate will override. It kind of depends on the situation, so I can't really tell you in which situation. You have to look at the makeup of the rock. Continental to ocean. Ocean always is more dense, so it will subduct. Continental is always less dense, so it will override. It will go on top. And continental to continental, no subduction. So no volcanic mountains. Just regular mountains. So you will get volcanic mountains in these two examples here. Okay, and then you're going to use page 5 of your reference table to go over these questions, and I will eventually post an answer key. But while we have a little bit of time, let's see. I know Google Earth takes forever to open, and it probably will. So I will have it ready for our lesson on Friday to go over this. So hopefully this helped, and you're able to do your notes. And I will see you soon Friday for a quick lesson on the dynamic crust. Bye-bye.